Alright, the transport ISN 1648-4142, TNDFonline.com, Taylor and Francis Group, Electrodynamic Braking High Speed Rail Transport, and then Electrodynamic Braking High Speed Rail Transport, receive, May 2000, Transport 2007, Volume 1, 22, Number 3, 178, 130, 178, 186. Abstract. The paper consists of the electrodynamic braking, which is particularly important with the high-speed railway transportation through theoretical technical perspectives. Braking methods use the high-speed train, which ensure the capability to produce redundancy of the braking system, include with the mechanical method based on additional friction disc to the wheel set, as well as the magnetic braking with the currently implemented based on eddy currents, etc. High-speed training of the ACDC, for which the principle of electric braking can be applied. Electrodynamic braking is in particular important high-speed transport linear motors developing speed with a 400 to 500 kilometers an hour traction. Rolling stocks will now have commonly used truck tests are in areas being conducted in Japan and Germany now. The papers suggest the theoretical practical solution to these problems, schematic diagrams, locomotive braking, ways of controlling braking force, verifying electrical circuit parameters are presented by the author, suggest the contact-free regulation of braking rheostat resistors for control of the braking force of the rheostat braking schematic diagram, harmonizing electrified railway power system operating aimed to ensure power regeneration is also presented. Keywords: voltage, contact system control, current, braking force, movement, inverter, power system, braking resistor, electrodynamic braking. Introduction. Prepare to start the construction of the European Railway link with the European Union states of Scandinavia countries, Viva Poland, Lithuania, Latvia, Estonia, and purchasing high-speed railway lines such as Siemens, diesel locomotive SCADA, two stored trains, trams, Vilnius, as well as upgrading old model specialists who the politicians should provide with more knowledge in electrodynamic braking and advantage of the disadvantage, also necessary to define possible obstacles, track circuits, and to provide some of the compensating technical measure for the theoretical particular knowledge of the discussed area be useful with adopting strategic development projects which should not become obsolete. For 50 years, the advantage of electrodynamic braking should be taken into account with the planning and integration of lithium in European Union's railway system. So far, theoretical principles of electrodynamic braking system have been thoroughly investigated, particularly with the AC traction motors, which are now introduced by famous rolling stock manufacturers Siemens, Bombard, Transport, Alstom, Mitsubishi Electric, etc. Most of the existing power systems are not well prepared to accept regenerative braking systems, returning energy to the power system. Indicative electrodynamic braking have been fully assessed since they were when common pneumatic braking system required with a compressed air with obtained with expensive of power needed to rotate compressors are used. Some of the elements of the system level the deteriorating addition of the pneumatic cylinders for storing compressed air with the other equipment required for the power up to 10 milliwatts per locomotive. Developing of the traction mode can be used in braking mode without any restrictions. An essential difference between electrodynamic and a traditional mechanical pneumatic braking used for up about 100 years for the control of the braking force, adjusting electrical parameters of the traction motor. Are the impact electrodynamic braking automation, technical mechanics, telemechanics as well, but the communication alarm system, including automatic block system, has not been accurately determined yet. The influence of the braking current over the rail circuit has not been widely discussed in the present paper. Method of electrodynamic braking, which speed with the rolling stock and creep of the braking with the block, but come with an effect with the side with not fully automated with a high-speed train with the redundancy of all of the available brake system required with the implying with electrical braking automatically replaced by the pneumatic braking system, vice versa. Therefore, interest with the electrodynamic braking method is continually growing with the methods are aimed to change with the operation of the traction motors of the locomotive into the generator mode, operation electrical motor, operator generator mode, convert with the kinetic energy of the locomotive electrical power, determine the type of electrical braking, which may be aerostatic, regenerated, dependent on the further use of electrodynamic braking does not eliminate brakes with the blocks. The use of the electrodynamic braking, for example, the unavoidable underground railways have been commonly used with the braking course of the dust formation, thereby polluting the air with the underground tunnel. Therefore, There are some special requirements for the ventilation system and for the training, etc. Electric braking may be divided into the rheostatic E with the low speed range, although the theoretically complete stop of the train regenerative use for the high speed rail range electrical chains in particular. In the case of electrical traction regenerative rheostatic braking, U the method allowed with electrical braking to be used with the braking initiation up to the full stop of the train is moving at high speed. Main advantage of electrical braking with the precise with the regulation of the braking force with controlling the circuit parameters, high speed with stability with the system. Braking can be either with the engine drive or automatically with the later, with only be observed. Now, the Lithuanian integrated with the Trans-European Transport Network. The next step is to integrate with the ETEVS, the European Rail Traffic Management System, embracing the system of the GSMR, or Global System Mobile Communication Railways, GPS Global Positioning System, controlled by U.S. Defense Department, Galileo, European Satellite Navigation System, GLONASS, and then controlled by Russia, or the GNSS, Global Navigation Satellite System, etc. These major subsystems aim to control the European Union transport system primarily with the high-speed trans-European trains. Braking efforts makes an integral part of the control. 3. The requirements related with the electrodynamic braking system. Electro braking system shall satisfy the following requirements effective with the braking and chosen speed range, flexible, controllable automatic regulation system that's able to braking mode with an easily operated electrical drive and a high reliability. Electrodynamic has both advantage and disadvantage and specific feature for the braking of the one of the locomotive, taking into account with the braking force larger with the traction force based on all mechanical loss with the subtract with the traction submitted with an opening on the braking, longitudinal stability with the rolling stock with the sharply decrease with the making. The control of the brakes more complicated with the locomotive driver, therefore process for the control microprocessor under the supervision of the locomotive driver. The braking force is concentrated. The locomotive wheel set with the power concentration as well as the power loss due to the drag friction shall sharply increase. Regenerative braking. Regenerative braking is more effective because the power given the control system is used with another electrical train return to the power system. More than 25% of the power used with the traction motor can be regenerated to the contact system. Circulation DC motor, most commonly used with the traction, cannot operate during regenerative braking. We cover the external load with the degree of the speed of the armature revolution, and increase with the stepwise theoretically up to infinity. The condition of the motor idle to exceed point no with the base of zero, m with the base of 0. The torque speed characteristic of the n is equal to the function of m, which require that the regenerative braking cannot be satisfied. The excitation winding of such motor should be shifted to the independent power system. In this the case, the excitation winding is powered with separated with the electrical motor semiconductor power source. Under the condition of the moment of resistance is m with the base subscript s is equal to 0. Motor reaches the ideal no load. No load is subscript 0, and show the regenerative and tractive effort on moment of resistance. Torque speed characteristic excitation motors, braking traction mode of the no load of the ideal no load speed. The UT is the contact with the system voltage IM and the armature with the current with the traction motor. Disregard the loss of the due to friction of the electric with the motor idle. Running of the electric motor forward for the motor is equal to the contact system voltage with the source supply with the contact system. When load moment changes, when the locomotive is moving down the slope, the speed and the speed of the no load motor armature exceeds no load. AMF is with the motor of the E exceed the network voltage armature current reverse electromagnetic moment of the developed in figure 1. Motor gives the generator mode with electromagnetic moment with the counter torque with respect to the armature because of the braking moment. The power produced for the generator is given to the contact system. In this way, with the main condition regenerative braking, according to the voltage electric train motor operating with the generator motor must be higher than the contact system voltage satisfied. Power of modern electrical trains like TGV is from France and ICE and in Germany. Motor car human electrical locomotive of 10 milliwatts therefore will become horsepower with very high may be found with a power balance equal equation where mechanical power of the motor shaft is equal to electrical power given the electrical supply network plus the denoted total power loss electrical circuit of the motor W. Therefore, the power returned during the regenerative braking should be with another traction locomotive unless there is no other train that is found with a particular section of the contact system. There is no regeneration. Current with the flow of the electrical braking does not work. It is inadmissible the mode of the rail transport. In this case, some of the specific requirements related to the power system, in particular regenerative braking power, should be returned to the substation transformer power system and by specially installed inverters are used by ballast resistors. In later cases, the regenerated power adds electrical energy sources. Most electrified railway to develop the country of Europe and America and Asia. Power can be returned with electrical power system supply with the use during the regenerated braking. Some of the older electrical railway upgrade of the installing automatically operating inverters should return with excess of the power of the contact system electrical power system. If there are no other train can cause use over the traction, so it should not be low ballast resist for the substation. Returning engineering energy electrical power system braking indicate the respectable availability of the absence of electrical locomotive and of an electrical locomotive. Others suggest upgrading the traction substation common electrical power system, installing current inverters help return the electrical power system instead of the ballast resistors where energy is lost where there is no electrical locomotive to use. See Figure 2.5. The key elements suggest the scheme of the transformer, substation control, rectifier, inverters, high-speed DC brake units. According to above scheme, all engineering obtained with the regenerated braking will be used in traction to return electrical power system. Alright, then Figure 2 shows the scheme of linking electrical power system and electrified, the high-speed brake unit, and the rectifier inverter, and then supplemental transformer, supplemental power supply. The operator's shown excitation generators during the regenerated braking is usually reliable for the function UR is equal to function IST. The C Figure 1. Figure 3 Curve 1 is not acceptable electrical mode because of the consider the variation braking force caused by the variation constant system voltage. This is because of the actually voltage of the power supply contact varies largely extent. The external character of the generator should be sharply dropped. Characters to ABC in Figure 3 and Curve 2 should be avoided. Impact contact system voltage variation braking force motor armature current with appropriate excitation method. The traction motor should be used with the contact system voltage change. Figure 3 shows the regenerated braking control using special excitation generator with characteristics A, B, and C. A circuit appropriate excitation with a motor with during regenerated braking obtained with a usually special excitation generated windings directed oppositely. See Figure 4. When the contact system decreases the regenerative current and increase the excitation generator of ZG will work demagnetizing mode due to the opposite of the direction action magnetomotive forces of the winding 6 and 2, see current direction in Figure 4. Figure 4 show the DC power regenerative force. Connection to traction motor special excitation generator during regenerative braking 1. The traction motor 2. The traction motor excitation winding 3. The control resistor 4 resistors. The 6 excitation windings opposite direct with the magnetic force of the DC mixed excitation generator. Current direct windings 4 and 6. Figure 4, 5 an excitation generator. I the subscript M armature regenerative current for the traction motor operating generator mode. IZ excitation current with the traction motor operating generator mode. Some of the situation can be observed with the voltage of the contact system increase with the characteristics reflect the chain of the braking force caused by the variation constant voltage special type of excitation generator is not used. The characteristics too show the chain of the braking force when special excitation generator is used during regenerative braking. See Figure 3. Rheostatic braking. Rheostatic braking 6. Traction motors operate with the DC series separated generating excitation mode with a series of the excitation generators used with the more electrical traction motors. Resistors are used starting and are used with the rheostat braking electrical locomotive drive with electrical. Rheostatic braking motors are feasible from both high and low armature speed with the low and low locomotive speeds because of the voltage traction motor operating with the generator mode does not depend on the supply voltage of the according it is required a braking force value depending on the locomotive speed when the go of the braking mode to go over the rheostatic braking force with the condition satisfied with the series traction motor should be disconnected. Contact system electric driven electric traction rolling stock from the generator diesel locomotive. Armature excitation winding should be connected with excitation current would not change its direction. See Figure 5, B, and C. Traction motor should be connected with the dynamic braking resistor. Electric motor goes over the generator mode 4 with the armature current and changes the causing of the brake moment to occur the direction of the moment. See moments M in Figure 5 of the terminal armature with exciting windings are not chained with the DC series winding motor will be demagnetized. Residual magnetism will be canceled out when armature current changes direction. As a result, the electric motor will not be able to operate series generator mode. When circuits armature with excitation windings are shifted according with the diagram B and C. In Figure 5, the direct excitation motor remains unchanged, resulting steady excitation state due to the residual magnetism, braking and rheostat, electrical traction, rolling stock, several stages with independent adjustments of the contactor showing separate elements, type of the control coil with a few different disadvantages. Many of them begin step adjustment with the rheostat, resistor step adjustment, braking current, braking force, greater number of large size communicators. The locomotive braking force can be adjusted for the controlling braking current and traction of the traction motor. Usually, the resistor which are used for the traction are employed. Rheostatic braking over the electrical traction rolling stock will achieve the highest speed uniformity start with the rheostat divided in separate stages. See Figure 6. Braking the train and railway traffic should be in control of the implying braking force, which could show Figure 5 shows the dynamic diagram showing the DC motor traction changing over to dynamic rheostat braking mode. A motor operated B dynamic braking mode with excitation winding shifted to ZA. And then C, the dynamic braking mode of the armature winding shifted. Shows DC motor and traction, the braking resistor, and the DC motor dynamic braking resistor. Figure 6 shows a circuit diagram of the rheostat with the traction mode of the DC series of excitation motor A and speed torque characteristics of N with the function of M of the B is RP1, RP2, and RP3 additional resistance of 1, 2, 3, and 4. DC motor traction show the 3 resistors, 1, 2, 3, and the capacitors. With armature motor E with the ZA speed characteristics traction show the minimum and maximum 1, 2, and 3, and 4, and then the into account all variables relating to the braking, which could be adjusted depending on the variation of the locomotive speed with the rolling stock, with the roadway profile, etc. should be developed. Otherwise, braking force could be insufficient stop of the train in time, and might lead to failures, catastrophe, and industrial equipment. The braking with electric motors usually uncontrolled is RS constant suggested single rheostat RP Figure 7 impulse with resistor regulation semiconductor device with thigh resistor IGB transistor operating key mode achieve automatic dynamic braking. Figure 7 show the circuit diagram thigh resistor U the pulse regulation brake rheostat resistor VS7 CKLK DMRM DK elements forth with the resistor VS1 communication UM power of the supply source force communicating circuits. The thigh resistor communicated with the commutation period remains unchanged, while the relationship between the duration disabling and enabling the state of the thigh resistor of VS1 varies in C Figure 8. In other words, the width of the disabling pulse is being changed with the method of regulating brake resistors as electrical circuit parameters referred to as width. Pulse modulation, another method called pulse frequency modulation, could be used within this case. The constant thigh resistor VS1 computation period. TK, sweet subgrade K with the commutation frequency changed by the change of the disabling period with the thigh resistor rheostat resistance can be smooth chain with the peak value of the RP is equal to 0. Figure 8 shows the diagram showing the rheostatic braking circuit parameter of resistor during pulse regulation and braking current. Now, the impact relations between the duration disabling and enabling resistor of the VS1 state with equivalent resistance of the quasi-steady state that should be determined. The resistance can be obtained with the following expression. R subscript EKV is equal to E over IVID, which is the average value enabling current of the armature circuit. And it can be found as the average current value of the communication period of the thyristor and give the equation for that, whereas the instant value of the armature circuit with the ISZD and ATV stands instantaneous value of armature circuit current with enabling disabling state with the thyristor variation circuit disabling current can be expressed as in the following two equations 4 and 5. When I use ED over E over the RO plus over R plus O subscript O and RP, steady current value with the thigh resistor ZS1 conducts current IATV over the E and over the RO plus RP, steady current value when the resistor Z1 is disabled, the circuit is disconnected. The I minimum, the current AM minimum and maximum can be obtained with equations 4 and 5, substituting T of T U Z D equation 4 and T equal to T A of T of equation A V. Equation 5 substitution values of the current of the minimum and maximum equation we get, and the expression contained can be simplified because of the circuit parameters chosen in such a way that the communication period TK is much shorter with the time constant of TATB at times. I don't know what double greater than armature circuit with the RP connect with additional TUZD greater than EABTB, TK UZD under such condition TUZ 2UZD TATB TABB USD. Therefore, deviation instantaneous current for the average value of the insufficient, with implying with the pulse of the current is low. On the other hand, taking into account the relationship between we change the exponent function power series in equation 8, leaving only the first two members of the series. Substituting IUZ, IATV, TUZ, and ATV in the equation, taking into account that ATV is equal to TK minus TUZD, we get IVD is equal to TKE over TKRO plus TK minus TUZ to the times RP. Then see that REKV is equal to RO plus 1 minus whatever the Y, RP, and equivalent additional resistor character for the control parameter. This change of the disabling the resistor equivalent breaking rheostat can be changed from RP to 0. The above statement is valued only with the infinity of the RP value. Does not hold for the RP is equal to result of an infinity when the connection additional resistor is equivalent circuit interruption. Analyze performed allowed with the conclude with the changing pulse ratio turns changes of the braking current braking force can regulate with the required accuracy. Using above method, the main parameter of braking for the rheostat resistor changing with the described regulation principle, but the same apply with the braking current, braking force, high accuracy, braking force regulation can be achieved due to the high speed system using semiconductor element thigh resistor IGBT transistor thigh resistor communication frequency is greater than 20,000 hertz. They're using a traction motor rheostat diesel locomotive braking to feed with the excitation windings with a traction motor connected series allowed with a circuit with a separate excitation rheostat motor braking to be made with excitation series. Some of the series with excitation motors are disconnected from the power source generator. Winding with their armature connected with the individual braking rheostat can be achieved with the setting of the brake of the regulator with the control of the mode with electrical braking, which says P connected with the armature windings 1 and 6 with the traction motor individual rheostat. Resistors usually not regulated with it during the braking method of the rheostat regulation suggested by the author's present paper that applied with the control of the rheostatic braking to diesel locomotive. While excitation motors winding 1 through 6 are connected with a series linked up with the output voltage synchronizing traction generator rectifier. Develop rheostatic braking circuit. The design helps to continuous control speed, braking force, wide range methods, while the even the diesel locomotive AC and DC electric motors. Figure 9 shows a circuit diagram of electrical diesel locomotive with the braking, synchronizing traction, alternator rectifier, L rectifier, RST, individual dynamic braking resistor K1 through K7, and started with the contactors 1 through 6 DC series excitation traction motors. SP would be your braking mode switch, and C1, C2's excitation windings of the particular traction motor. Braking force regulated changing electrical motor parameters found with an alternating excitation current traction generator should shaft revolution diesel generator is constant. Varying revolution diesel generator ND equals varying revolutions with excitement of the current traction generator constant. IZ the constant, and then this O with a slash through the constant lets us consider the technique of determining primary braking traction motor analyzing circuit presented in figure 10. Figure 10 shows the traction motor operating in rheostat braking mode, braking resistor, an electrical current traction generator constant at the resistor, and then the field of the traction motor. Electromagnetic moment to develop of the motor shaft that we express with the following: MST equal to CM over MST is equal to CM over N EM times IST, and then this circle O the magnetic pole current. CM of the PN over 2 pi A constant motor with the NEM coefficient mechanical magnetic law of the motor. P is the number of the pole pairs, and the N is the number of the armature winding contactors. A is the number of the parallel branches. IST of the motor armature for the braking current of the rheostatic braking. And the circle with a slash through the magnetic pole card WB with electric motor force traction motor operating generator mode. E is equal to C subscript E with the O with the N is obtained with the voltage balance equation. where CO with the P enter with 68 with the motor constant armature spreading speed RPM and the RST of the breaker resistor and the RN is the armature widening resistor additional pole with the total impedance of the braking resistor armature circuit, braking current expressed, and then the braking moment and directly opposite of the rotation motor armature expressed based in 13 following way. As seen in Formula 17 and 18, linear braking relation straight with the OA with the figure 11, the same with the acceleration flux with the concept of the hyperbolic relationship between the braking moment, armature speed with the moment established for the constant obtained with the diesel locomotive braking character with the relation between the braking force with the wheel set rolling surface, locomotive speed following formulas for the used, where the U is the gear ratio with the gear drive, with the D is the wheel set with the diameter, the M is the number of the traction motor, and with the subscript is for the gear drive. The efficiency locomotive speed in kilometers is expressed as V is equal to 0.18 over wheel set with gear drive over the gear ratio taken account with the following formulas. By using above formulas being character for the diesel locomotive, BST is the function of V, which becomes obtained with acceleration flux, constant braking force, proportional speed depicted with a straight line beginning with the origin coordinates with the braking constant of the inversely proportional speed with a hyperbolic function C curve AD in figure 11. Failure strongest traction motor acceleration currents defined below under region OA with the braking characteristics. And then figure 11 shows the braking carrier with the traction motor A, restriction imposed with the strongest acceleration current AD with the restriction imposed with the strongest armature current, AC restriction imposed with the communication BSV with the restriction imposed with the adhesion of the rail with the key IM. Or the magnitude of strongest traction motor acceleration short-term and long-term flux defined with the boundary with AD with the braking characteristic that determine the limiting temperature of the motor's armature winding with the braking rheostat with the speed with the high braking force restrict with the condition computation with the curve HC with the traction motor collector with the curve CE restriction braking force imposed on the condition of the rail follows the relationship between the adhesion cohesion and the speed with the curve of the KM and the analyzed braking characteristics shown with the braking force regulated by varying current and acceleration flux of the daily braking force that can be attained with the speeding varying to obtain the required braking characteristics of the locomotive with automatic system ARS controlling speed braking force with the system maintaining feedback with controlled magnitude braking force changing braking current or acceleration flux. The circuit is so that the braking force can be controlled with the locomotive down the slope of the constant slow down speed. V is the constant up complete stopping. In other case of the braking in order to slow down the locomotive speed according to the light signal depending on the type of the characteristics. In this case, emergency braking force regulated according to the highest value of the armature current with the acceleration current limiting the communication condition. For the conclusion, the electromagnetic braking high-speed transfer main method ensuring the stability of the braking process. High accuracy braking force regulates the creep of the longitudinal dynamic force developed in the stepwise of the pneumatic braking. Electrical dynamic braking control system effectively integrated with the global transport control system. For electrical dynamic braking is introduced economic indices of the indexes of the system considerably improve the use of the modern microprocessor control system. Regeneration braking high-speed train under the condition of heavy railway traffic allows 25 to 40% of electrical power to be returned. The powers if the power stored with the traction fully utilized with rheostatic braking. The required braking force can be obtained with a wide range regeneration braking due to the high speed range of the rheostatic braking low speed range. Mechanical braking commonly used now should be kept in reserve. The technique to play with the main braking method is usually complete stop of the locomotive speed with 5 to 2 kilometers an hour. An advanced method of the braking force control of the rheostatic braking uniformly chain with the main circuit parameter of the rheostatic resistor value with the non-contact ways of means of the semiconductor switch of the digestive scheme and the upgrading electrical power system. The aim of the return of the power obtained with the regenerated braking system is offered. Scheme braking force stabilization, regenerated braking contact system voltage is presented. Electrodynamic braking specified acceleration, in this case acceleration value with negative to ensure that helping to avoid action of the electrical dynamic braking force on rolling stock. In this way, the deterioration elements of the automatic clutches chassis is reduced while traveling condition. And the passenger becomes more comfortable because of jerking is limited power stored with the locomotive traction completely utilized. The power is obtained with the burning oil with the diesel locomotive obtained with electrical power reaching more than 10 milliwatts. Utilized by electrical locomotive electrical trains. The power consumption of the later is very high, but the ordinary mechanical braking is applied. No useful work is done by powers not used by braking, and they show the references. And this was a reading of your Electrodynamic Braking High Speed Rail by Taylor and Francis Group, and this was actually published as Transport 207, Volume 22, Number 3, 178 through 186, Electrodynamic Braking High Speed Rail Transport.